Hello, thank you so much for tuning into my YouTube channel. Today's video is going to be a tutorial on a spectral reflectance reconstruction from RGB camera response using interpolation technique. There are so many methods using which you could recover a spectral reflectance from RGB camera response, but in this video I want to show you how we could use interpolation. Let's get started. As I said in this video, I want to talk about spectral reflectance reconstruction from RGB digital camera using linear interpolation technique. Interpolation approaches are regarded as statistical methods and are abundantly utilized in some engineering fields such as color engineering. The approaches are commonly used when the relationship between two sets of data are very intricate that other statistical techniques cannot yield precise answers. Among diverse approaches for interpolation of the scattered data, the linear triangular or tetrahedral interpolation method can be highlighted. This interpolation method is composed of two steps. The scattered points of the dataset are triangulated, which happens in two-dimensional planes, tetrahedrized, which happens in 3D spaces, or tessellated, which happens in n-dimensional spaces. And then the interpolation is carried out inside each triangle or tetrahedron or hypertetrahedron. In such approaches, a given point in the 3D space can be partitioned with many different procedures of tetrahedrization. Delaunay tetrahedrization is the most appropriate method in which tetrahedrization is attained through connection of all the nearby points in the Voronoi diagram of a given dataset. The Voronoi tessellation partitions the space into a complete and disjoint set of tiles where each tile Ti contains one point Xi of the given point set. The tile Ti is characterized as the area which is nearer to the scatter point Xi as compared to any other scatter points. Here, the xxi and the xxj marks the Euclidean distance between the points. In the case of three-dimensional interpolation, an assumption is made that the scattered points xi, yi, zi are tetrahedrized utilizing the Delaunay tetrahedrization approach. Each of the tetrahedrons serves to interpolate any arbitrary point inside of it. Four vertices P1, P2, P3, and P4 of such tetrahedron are given in the locations x1, y1, z1, x2, y2, z2, x3, y3, z3, and x4, y4, z4 of corresponding four vertices, whose values are the color values at point P located in x, y, z in the tetrahedron can be calculated through the linear interpolation polynomial as shown here. Then the coefficients a, b, c, and d can be obtained by solving the linear system of equations as shown here. Accordingly, the R value at point P located in x, y, z inside the tetrahedron can be calculated by this equation. The weights a, b, c, and d are called bicentric coordinates of the point P in the tetrahedron P1, P2, P3, P4. The coefficients a, b, c, and d can be computed through the matrix equation as demonstrated here. So here we are trying to recover the spectral reflectance from RGB values. So the target point has the RGB values of RGB and the other 4 points surrounding it have values of R1, G1, B1, R2, G2, B2, R3, G3, B3, R4, G4, and B4. We are also using the 3D interpolation method explained here. So this last equation here can be rewritten as shown here. So the spectral reflectance of the target point is estimated using this equation. This is how we estimate the coefficients a, b, c, d, and then we use that to estimate the spectral reflectance of the target point. Here's a quick visualization that helps you understand this method better. You can see that the target point is in the middle of the tetrahedron made by the points P1, P2, P3, and P4. For these 4 points, we know their values of RGB and spectral reflectances. We can use interpolation as shown before to estimate the spectral reflectance of the target point from its RGB values. It is clear that if the target point falls outside the tetrahedron, interpolation technique cannot be used to estimate its spectral reflectance. Interpolation technique is a powerful method, but you need to make sure that the point falls inside the tetrahedron made by the training samples, otherwise you need to use other methods. For this work, I am using these color charts. This is MATLAB Color Checker SG, and this is MATLAB Color Checker Passport they call it, or X-Rite, and also this is a color chart made out of artist paints. So to do this work, I'm going to be simulating the sRGB values. I first obtain the mean spectral reflectance for each patch, or mean patch values. So this is the matrix that contains my spectral reflectance, whose size is m by n. M is the number of wavelengths and n is the number of patches. And then I convert that into xyz using this formula. K is a normalizing factor, xyz is the color matching function of the standard observer, D65 is the light source that I'm going to be using, and here it denotes the spectral power distribution of the standard illuminant, and R is the spectral reflectance as shown here. And then I convert the XYZ into sRGB, and I consider that to be the RGB response of my supposed camera. Okay, let's go to MATLAB to show you an example code. Okay, here are the programs for this video. First, I'm going to be loading those color charts that I showed you, and then this is the script that contains all the data that I need, like the spectral power distribution of the standard illuminant and the color matching functions of the standard observer. Here I'm converting the reflectance into XYZ, and then I'm converting them into sRGB. To convert the XYZ into sRGB, I'm using this function which uses the standard formulae to do so. And you could also have access to all the codes here using the link in the description section of this video, so don't worry about that. So the same thing for the other two color charts, and I'm going to be plotting them in the 3D space just to show you where they are located with respect to one another. And that will be the first script. Let's run this. As you can see, here are the points in sRGB color space. So my first color chart has 130 samples or 130 patches, and my second one has 140, and the third one has 24. And these are all of them. So now I have to split this data into two, training and testing. The testing points would be my target points, and they have to be located inside the gamut made by the training samples. So in the next script, I'm going to be choosing points from inside the gamut made by these points. And those will be my target points, and I would estimate the spectral reflectance using the rest of the samples. Let's go to the second script. So first I'm going to be combining all the data, and then I'm going to create a Delaunay triangulation object for a 3D convex hull. And then I'm going to be choosing points from inside the convex. And then I'm going to show you guys what happens. So here is where we're going to be checking if the point is inside the tetrahedron or not. Let's run this. So here is the result. Let me make it bigger. So you could see that those magenta ones, they are my testing samples. And the cyan ones are my training samples. As you can see, they are located inside the gamut made by the training samples. Because for interpolation technique, you gotta make sure that your samples are inside the gamut, otherwise you can't use that method. Okay, now we have our testing and training samples. Now the last script would estimate the spectral reflectance of the testing sample using the spectral reflectance of the training samples. So now we have some target points which are my testing points, and I'm going to use the training points to estimate the testing point spectral reflectance. So this is where I'm going to be making the Delaunay triangulation again, and I'm going to be using the training samples for that. And then here I'm going to be locating the testing sample inside the convex made by the training samples. And I'm going to also find the bicentric coefficients. And then here we specify which of the target points are inside the convex, or which of the testing samples are inside the convex made by the training samples. Then here we estimate the spectral reflectance of the testing samples inside the convex made by the training samples. And then here we calculating the mean RMSE between the true spectral reflectance and the reflectance estimated for the testing samples. And here we calculating the color difference. To do that, we first convert the reflectance values into XYZ and then XYZ into CLAB values. And to convert the XYZ into CLAB values, we use this function. And again, you could have access to these codes using the link in the description section of my video. So here we're calculating the color difference between the spectral reflectance estimated and the original spectral reflectance. And here we're going to be visualizing those spectral reflectance in sRGB color space. And that's it. Let's run this script as well. So here it is. This is the mean RMSE between the original and the estimated spectral reflectance. And this is the mean color difference between the original and the estimated spectral reflectance. The color difference is calculated using CIE-DE 2000. And as you can see, this is the estimated and the original spectral reflectance. And I'm just visualizing that in the sRGB color space. You can see that this gray patch doesn't match the original very well, but the others have not been too bad. And you can see that the mean RMSE is not that bad at all, and same with the mean color difference. And that's about it. Thank you so much for watching this video. I hope you liked it and you were able to get something out of it. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you so much and have a nice day.